Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture 12. Okay, this is basically lecture 11. Sorry. Now we are dealing with the design and analysis of column C1. Okay. Finally, we reached to the design of column. Okay. We designed basically the beam in the previous lecture 10. I summarize. Okay, and we did all the calculations. You see how to use this formula to and how to use this is, I think so, will be a new approach for you people. Remember how we can cut up the bars. Okay, if you are cutting 2 bars, then you find out the percentages. Okay, like if you are cutting 2 bars basically, so you multiply 2 with this 0.785, you got that percentage, remember. And then you will the percentage will be increases or decreases. You search here and just extend the line and find out the fraction distance. Okay, so this is a new approach. Okay, I think you will see this first time. Okay, and we also designed the shear reinforcement. Okay, and now we are designing the column. Okay, so what we have basically, I will explain. Remember, this is our columns. Okay, you see we have 4 columns, but the good news is that the columns are axially loaded column, not eccentric loaded column. Okay, because you see 20 feet and 20 feet, 20 feet and 20 feet. So this is the beauty, you can say. This beam is also 20 feet, this beam is also 20 feet, this beam is also 20, and this beam. Similarly for all other columns. So therefore, I choose the column as C1. Clear? Now, basically we all know the loading. Most of the students basically, they are confused with the loading which is basically acting over the column, and they can't able to calculate loading of columns. Okay, remember, it is very simple. You see, the load is coming from the slab to the beam, and then beam transferring that load to the columns. So as the column is supporting 4 beams, that's why it will taking the load of these 4 beams, and these 4 beams basically transferring the load to this column. Let me show you this video that I will explain that how important the design of column is. Okay, here you see basically the column, like let me show you this column. Okay, you see, practically you see that there are 4 beams which is coming over this column, and since this is an axial column, because all the spacings are same, the most critical problem is occurred in the design of this column, that this column is buckle out. Remember, that is, there are excessive loading and it is buckle out right here. Okay, so this is the most dangerous failure. Remember, the column failure is the failure of the whole structure. Remember, and it is very crucial, remember, due to poor design of this column. Okay, so that's why we have to make sure that the capacity of the column should be such that can support the load coming from this beam. Okay, the load coming from that beam. Clear? And similarly the load coming from this beam, and similarly the load coming from that beam. Remember, this is the way we are calculating the load coming from that beam, that beam, that beam. And remember, this loading is very simple. The reaction which is basically calculated to this beam is we will reverse that reaction, and we say that is basically our loading to this column. Similarly, the reaction to that beam, similar reaction to that beam. Okay, and similarly reaction to this beam. That 4 reactions is basically calculated, and they're acting over this column. One important thing is that we have to count for the weight of the beam as well. Okay, and remember, we also count for the design of footing. Okay, so here we have basically, let me rub it Here we have, remember, the loading of these beams. Okay, so this is an axial column. Okay, now coming back, here you see we are providing 12 by 12 inch column, and the load of the beam on column you see 27.4 plus 23.9 and 2. This means that we have to go back to the shear diagram, and from that shear diagram we can find out these moments. Okay, here you see this is the column. Okay, and this is the one side beam, remember. Now you see this 27.4, which is reaction of this column to this span. This is end span, and this is also a reaction 23.23, which is reaction to the middle span. So you see the total loading will be how much? Remember, total reaction which is providing by the column to these two beams, basically from both sides, is 23 plus 27. Okay, so this is only from two sides. Now we have to counter for four sides. So that why we add these two, 27.4 plus 23.33, and multiply it with 2 to count for four sides. Clear? So this is the reasons behind that we are using that formula for calculating the load on the beam. Okay, we add up these two because this is for one side beam for end span and this is for middle span. Okay, and then we multiply with 2. Okay, you see here 23 from that side, 27 from this side, because this is the exterior face, and 23 from that side and 27 from that side. Okay, so adding these four reactions we got 102.6 kF, the total load for 16 feet length, which is the height of the column, and 12 by 12 inch column. Okay, so here we don't need to add basically the weight of the column, because the weight of the column helping us in design and footing. Okay, now this is a well-known formula. You all know this formula very well, I think so. Here in the Nelson book you see, and this. Okay, and 0.85 is the alpha factor, and remember 0.85 is used for spiral, while 0.80 is used for tight column, alpha value. Phi value is 0.75 for tight column and 0.65 for a 0.65 for a tight column and 0.75 for spiral column. Sorry, 0.75 for spiral and 0.65 for tight column. Okay, but here I am using what more a little bit larger value. Okay, because these are the new versions of ACI code. I am using the old one before 2000. Okay, alpha is 0.7, although you can use this one 0.65, and phi value 0.8, which is okay. Oh, clear? And I am using, because we all know that the limitation of steel reinforcement according to ACI code, that your rho provided should be greater than rho minimum, clear, and should be less than rho max. Now this is ductility, and you see we provide rho provided from 1% to 8%. This is a limitation. Okay, because if you are increasing the percentage of steel, this may cause congestion into the column. So we are using the steel ratio 0.01, and you see AS will be 0.01% of AG. Okay, and it gave me 1.44. So I just plug all the values. I have AG because my column section is 12 by 12. Okay, so that why my AG is 144 minus 1 point, that is AST. Do all the calculation, you got 320 kF, which is greater than PU, so we are okay. Okay, the column capacity is okay for this amount of reinforcement. Remember, you are providing A is minimum, that is how much? That is 1.44. Now if you need number of bars, so just 1.44 divided by number 4, that is I think so 0.19 and something. Okay, it will give you how much bars using number let me check it. Okay, let me check it. this is a 1.44 divided by 0.2, let's say. So I have, let me do it again, 1.44 divided by 0.2 equals to 7.2. okay, so that is not enough. 7.2. so here I am using here I think so they are using dia bar is 6 by 8. okay, number 6 bar. Basically this is number 6 bar. Clear? This is number 6. 4 number 6 bar basically they were using. okay, so 4 number 6 bar, and this is designed for ties. You all know the design of ties, okay, very well, that we have to use design of ties. Remember, different pattern is possible. These are the ties pattern. okay, if the spacing in between two successive bars is less than 6, so we don't need these cross ties. But if this distance is more than 6 inches, so you need this kind of arrangement you see here. okay, so you have to provide it. okay, and tie, you see number 3 for number 10 and less, and number 4 tie with for number 11 and larger, this one. And for tie spacing, okay, tie spacing should not be exceeded 16 times dia bar of the longitudinal bar, 48 times of tie bar, okay, and smallest dimension of the member, that is 12 inches. So here I am using again same checking 16 times of dia bar. So here we have 6 divided by 8 times 16. This is basically 16, not 12. okay, this is not 12, this is 16. okay, please make correction. So 4 and this is 6. Clear? And do the calculation. okay, what you got, this is 16 basically, not 12. So let me check it. 16 times 6 equals divided by 8 equals, it give me 12. okay, it give me, yes, 12. So this is 12, please check it. And 48 times die of stirrup, so this is die, we are using number 4 tie, although this should be number 3. okay, because if the main bar dia is more than 11 or more than 11, so we use number 3, but although you can use it. okay, and 48 times die of tie, okay, you see, you do the calculation, and 12 inches. So here we are using 9 inch, but check it, this calculation. okay, this is 16 times dia a bar. okay, let me check again. 16 times 6, okay, equals divided by 8. I got the value, that is 12. okay, this is 12. So 12, this can be used 12, but remember, use 9 inch center to center, that will be more conservative. Clear? This will be more conservative approach. So this ends up the design of the column. okay, and the diagram is clear right now, you see here. okay, I think the column design will be clear, there is confusion. okay, in next lecture inshallah we will design the footing for this column. okay, and yes, that inshallah will wind up things. okay, so see you, okay, in next lecture. Thank you for watching.